Hello friends, welcome to Abaqus Acumen for quick and sound learning. In this video, I will show you how to build a SPH modeling in Abaqus. For that, we are taking example of a water droplet impacting on a membrane plate. So as you see on your screen, water droplet which is moved in a vertical G direction, that is negative G direction, and it is impacting on a thin membrane plate. And you see how the displacement that is propagating. In the similar way, we can also see a stress propagation. So this is how the stress being propagated on a thin film with a water droplet impact. In this video, I will show you how to build this simulation in SPH using the SPH modeling capability in Abaqus CAE software. So we are using the Abaqus CAE 6.12 software, and I will show you all the steps involved in right from geometry modeling, creating a job with explicit dynamic steps. So everything I will show in this video, so that once you see this video, you should be able to do this exercise on your own, and with this learning you can leverage this process or the method to your own applications using the SPH capabilities. So let's start. I will just give you a background first. What is we are trying to model over here. Okay, so this is a problem definition. We have a simple membrane plate, okay, planar membrane plate with a thickness of 1 millimeter, and the size is 60 by 90 by 60 millimeter, and we have a droplet which is modeled as SPH particles, and this droplet is being impacted on this thin film with a velocity of 5000 millimeters per second, which is equivalent to somewhere around 18 kilometers per hour. And this is kind of a water jet impacting on a membrane. So for this, we are using Abaqus CAE to build the FE model, and the unit system will be following is Newton, millimeter, second, and ton. Properties required for the simulations are the water properties, that is to define the SPH particle. The density is that is 1000 kg per meter cube, so the equivalent in ton per millimeter cube is 999 e raised to minus 12. And then we need the equation of state. So the equation of state we are defining with the property of speed of sound in water, that is 1400 meter per second. Of course, we will be converting this meter per second to have a consistent unit is 1400 e raised to 3 millimeter per second. And we have this plate membrane, so density is 1.8 e raised to minus 9. The unit is ton per millimeter cube, okay, and the elastic modulus is 510 MPa. So with this information, let's go back and start building FE model for this SPH simulation in Abaqus CAE 6.12. Okay, so let me clean up this screen, and we'll reproduce this FE model, and then we'll see the same simulation again after once we get the result. So to begin with, we'll start with modeling of droplet. Okay, so for that, go to create part. Droplet we are modeling as solid, so I'll be modeling first the section, and then we'll use this revolution to make a solid droplet part. So I'll use a create spline method. So approximately it is 15 millimeter in size, that is a width. So we'll use some approximate technique to model the droplet. So this is good enough, and then I will use a line to connect the top and the bottom points. For solid, we are going to have a 360 degree angle. See, okay, done. Geometry is done. So let me change the canvas color background so that the visibility is better. So let's go ahead and define the property to this droplet. So this is a very standard process in Abaqus CAE software. So we go to material manager, so we'll create SPH material mat density, here using 999 e raised to minus 12. So here you just define the mass density, and later on we will plug in the equation of state for the SPH material in input deck file. Okay, dismiss, go to section manager, say create. So here we are creating the solid section, dismiss, then assign these properties to the droplet geometry. Okay, so the properties has been assigned to the droplet geometry. Now you go and do a mesh part meshing. You can directly go to the meshing. So for that you have to choose tetra element. Okay, element type, done. So we will do for explicit linear. So remember guys, when we do a SPH modeling, and as this water droplet is being represented as the SPH particles, so what we need is a node definition. So even though we are using this as a tetra element to define or capture the geometry of the droplet, and later on in text editor we will take out this tetra element definition, and only we retain the nodes, corresponding nodes, and for those nodes we will define the as the particle elements. Okay, so to get that nodes with inside this droplet geometry, we need to first mesh it with a regular tet element. Okay, yes, and remember this is to choose the explicit and linear and 3D strious. So okay, and then make sure that we have this C3D4 linear tetrahedron element. If you want to have a more finer nodes or more particles within this geometry, then you can go ahead and do a quadratic with a higher number of nodes. Okay, so as of now, to restrict CPU time, we are just using the linear option, and then C3D4 as a tetrahedron element. Okay, so I will choose 2 millimeter. Okay, so this is good enough for our exercise. Now we will create a node set using the nodes of the droplet. So just go and say create, and here say droplet nodes. So this is an important step for us, so that once we create the node based set for the droplet nodes, so the same thing we will use it for defining the velocity as well as initial velocity for this droplet, and the surface of this droplet for the contact definition. So here I will say droplet node set, say choose node, continue, done. Okay, I have jotted down the steps which we need to carry in Abaqus CAE, and so this model we are going to build in 2 stages. In first stage we are using the Abaqus CAE software and do all these steps, that is 1 to 12, like creating SPH part and then assigning properties, then creating the mass elements. So these are the steps we need to follow, and then once we write the input deck from these steps, we will do a second stage activity, that is we need to carry out a few critical steps in input deck in text editor. Then the complete FE model deck is ready for submitting the solver. So let me go back and see where we stand now. So we have created the SPH part geometry, then we defined the material properties, we did the meshing, and then we did create the SPH particle. So now we are going to use create a mass elements using the droplet nodes. Okay, so let's do a mass element using the droplet node. For that you go to the property module, say special inertia, then say create, and here you say mass elements. Alright, say continue, and here we have to choose the drop node. So remember guys, we have to use this drop nodes. That's something we created before. Continue, and put some dummy mass value, that is 1 kg here I'm using, maybe 1 ton you can say here due to the unit consistency, so that doesn't matter anyhow. So say okay. So you can see the green color dots, so that means the mass elements has been created using those nodes. Okay, let me go back and see the next step. So now we will move on to creating the bottom plate, that is a membrane plate. Okay, so for that, go to part, say create, here you say membrane, so this is deformable, this is planar shell. Continue. So here I will use the create point method to have this rectangular membrane plate. So I will use this coordinate system. So you can choose, if you are familiar with any other method, you can go ahead and create as per your method which you are comfortable to do, but here for this exercise I am going with creating the points and then using the line command to create a plate out of it. Okay, so I will put it now. Here I will key in the coordinates. So I'm assuming the center is uh, at the center of the plate, so that means the center is somewhere over here. Okay, and up according to that center point I will define the x and y coordinates to generate 4 corner points, and then I will use those 4 corner to create a plate membrane. Okay, here it is. Now you go to property, say create. So this is membrane, matte membrane. Define the density. So the density is 1.8 e raised to minus 9. Then elastic properties, so I'm going with 510 millimeter 510 Newton per millimeter square, so that is 510 MPa, and the Poisson's ratio is 0.4. okay, so dismiss. Now we'll create a property, solid shell membrane. So the thickness is 1.0 and we are choosing the material matte membrane. Okay, dismiss. So now we'll assign the properties for the geometry. Done. So let it be middle surface and the section is cell membrane. That's okay. Okay, so now we are defined the cell properties, the thickness and the material properties to this plate. So now I'll go to assembly and I will instance the membrane part. Okay, so go to assembly module, instance part, and instance the droplet part as well. Let's say okay. So you can see so okay, now we can see the plate and the plate membrane and the droplet are modeled. Now we'll position or this droplet in a in a positive G direction. So we'll go to rotate, select the instance, done. So we are going to rotate by 90 degrees. So the axis of rotation is X. So origin is 0 0. Define some positive X number, say 5.0, let's say, done. And the angle of rotation is 90. So just say OK. So guys, when we do this, you have to press the OK button, then only the action is get completed. So now we will translate slightly above the plate. So select the instance, and the origin is 0, and we are going to translate in Z direction. So it is 3 millimeter, or you can say 4 millimeter. Alright. Okay, so it is done. So position of instance is correct. Okay, so now we'll first mesh the plate, membrane plate. For that we have to select I will hide okay, make it independent. Okay, so now it is ready to mesh. Go to controls, chord or chord dominated, either is fine. Then meshed element type, choose the geometry, done. So we are interested in S4R. Okay, so that is fine. So this is reduced integration shell elements, chord elements, that is good for us. Then we'll define the element size. So let us try with 4 millimeter. Okay, we can, so this is good enough. So we'll move to the next activity. Let me see what is that. Let us go back. So let's refer this again. So where we are, so we have meshed the plate with the cell elements. Now we'll create a surface using this membrane plate elements. We'll use the same instance, say surface, say create, and this is mesh based. We'll have a name for the surface, that is this is master surface membrane. So choose it mesh, continue. So I will select all these elements, done. So I will choose the brown, because the water droplet is coming in negative G direction, so the normal has to be aligned to in that particular direction. So I will choose the brown. That's it. So we have created the surface. So let me go back and refer the step. So now the step definition, that is we'll define this explicit dynamic, and then we'll also look at some mask scaling options. So I don't think mask scaling option is required for this exercise. So we'll go to step, so create step, explicit dynamic, and choose explicit dynamic explicit, continue. And here I'm time period, I'm choosing 3 millisecond. So that is in seconds, it will be 3 e raised to minus 3. Okay, dismiss. Let me go back and see what is next step. So we are defining the initial velocity using droplet nodes. Okay, and then we'll apply BC also for the corner nodes of the membrane. So for that we'll go to load module, choose initial velocity. So here for that we'll have only the mesh part of droplet. We'll hide this and we'll show this part. Alright, and now we'll go back and define initial velocity. Choose velocity. So here we will go to set nodes. Okay, so as I mentioned, we need to choose the droplet nodes. Continue. V3, so this is minus 5000. Okay, done. So you can see the representation of initial velocity in negative z direction. Now we'll apply. We'll hide this instance and then we'll show this instance so that we can define the boundary conditions for the corner nodes. So using the shift button and then choose the corner points, say done. So I have chosen all the 4 corner points. So these 4 corner points or the corresponding nodes, we will fix it in all direction. Say done and custom. Okay, so you can see the symbol has appeared showing the 4 corner nodes are fixed. So where we are on the steps part, so we applied BC plate, we are applied or defined the initial velocity. So now we'll create a job. Okay, so we are create a job. We'll see the output definition. So for that you just go back to step just to relook at the output definition, and we will choose so you edit on the output definition, this output request window, and choose. So you might be seeing evenly spaced time interval. This is a default, so just change it to every x units of time. So we are requesting for 0.1 millisecond. Okay, so our total run time is 3 millisecond. So for every 0.1 millisecond we will be requesting the output, so that in the result you can see we can have the output for each of those time instant of every 0.1 milliseconds. So, okay, just say okay, and then you also go for history output with the same time interval should be sufficient. So by default you might be seeing this every n time increment. So now you'll go to x time, that is 1 e raised to minus 4. So just say okay. So now we are all set to write a input file. So go to job module. Okay, so we have create the name. So I will just delete it, I'll recreate it just to show you how to do it. So just go to job module and say create, say SPH drop, continue, just say okay, just leave it to all defaults. That's it. So we'll write an input file for this. Okay, so this is how we have to work on Abaqus CAE software, so that to create a SPH model. And now the second stage, we'll move on to second stage. So as I mentioned before, there are some tailoring activity or some editing portion is left out that we need to carry in text editor, and we have to follow this 1 to 7 steps to complete the FE model to submit the solver. Okay, so let us open the input deck file. Okay, so here is the input deck file open. Now I will follow. Let me see what are the activities I need to do in text editor. Okay, so the first step is we need to delete the solid elements, and then change the mass elements. Okay, let me do it. So I will so we need to define delete this C3D4 elements. So for that so you have to select it. So this is TextPad is a wonderful tool to do this operations. Shift delete. So we have deleted the elements, and then where to change the type to PC3D. So these are the particle element keyword PC3D. And then we will modify the solid section EL set. We will choose this. Then we have to define the characteristic length. Okay, so as this should be the half of the element size. Okay, so for the meshing of the SPH droplet geometry, we have used 2 millimeter as a mesh size. So we'll be using a characteristic length that is half of the mesh size, that is that is 1 millimeter. Okay, so 1.0 is your characteristic length. So this is very important definition. We have to do it over here. And for example, if your element size is 5 millimeter, then you have to have a characteristic length definition as 2.5 millimeter, so that the two particles have that having that characteristic length will cover the entire element, that is a distance between the two particle nodes. So this is 1.0. Then so let me go back and see what are the next step. So we have deleted the solid elements, and then we change to PC3D particle elements. So we already defined the solid sections. And then we also defined the characteristic length. So let me go and eliminate the star mass definition. Okay, so we change to type PC3D for that, and then we'll go to next. What is the definition? Sorry, this is down. So we'll delete the definition of mass element. So these are the dummy masses we created in Abaqus CAE. So we have to define the SPH properties. Okay, so let us star material. So this is the matte membrane. So here is the SPH material. So we have to define the equation of state over here. So I have plugin properties ready already. I prepared this, so you can, if you want, you can send us an email so that I can give you this information or input deck as well, so that you can refer this and do on your own or practice on your own. So this is a standard definition, that is equation of state for the water elements, water particles. Save it. And then we have to define node based surface. Okay, so we'll define the node based surface. So the tip is we have to define this in assembly portion. So guys, this is important point to note. So when you define a node based surface for the SPH particles, you have to define it in assembly portion. So I will show you how to do it. So let me pick the and remember, so when we choose the node set, so you go to this velocity, that is initial conditions, that is type velocity, and just copy this node set name. Okay, and then we'll use it. We'll go to assembly, in assembly we already defined another surface of membrane, so just say star surface. Okay, so just beneath this I will define the surface, node surface, that is a particle droplet surface based on the node set, star surface. So name is, say, slave particles, and type is node, and say, and we already copied the node set from the initial velocity, so this is a droplet, say comma, it's done. So next, last point is remaining, that is the definition of the contact. So for that we need name of the surfaces, so we'll pick from these keywords. So let me first type in the keywords, so that we're going to do it under the step somewhere here. Contact, star contact, inclusions. So we will now choose the master and slave. So the master membrane is, this is the name of the membrane surface, and then we have comma, the slave particles, so this is the name of the droplet surface, just say Control C, and here is Control V. So that's it. So rest of the things are already defined, so just say save this INP file, and then this is ready to submit to Abaqus solver. So guys, just go ahead and submit this run, so you'll be able to have a result. So let me bring in the results. So to save the time, I already have the results, so I will load those results. Okay, so here is okay, so here it is. So we can change it to displacement, so magnitude, let's say how the alright, so here it is. So this is how the membrane is deforming under the water droplet impact, and let me little slow it down to visualize. Yeah, so here you can see the droplet with initial velocity of 5000 millimeter per second is impacted on the thin film, membrane film, and you can see how the deformation is taking place. And now we can switch to the stress. So you can see now how the stress wave is propagating across membrane plate. So this is what I wanted to show you for this SPH modeling in Abaqus. So on top view, so this is the top view, so how the droplet is scattered all over. So guys, go ahead and see this video, refer this video time and again, so that till you get accurate. So I'm sure, so once we follow all the steps what I shown in this video, you should be able to get the simulation what I'm showing now, what we learned in this session. So all the best, and if you want to have the input deck for your reference, please email us on abacusacumen@gmail.com. If you find this video useful, so please go ahead and like us on YouTube, subscribe our channel, Abaqus Acumen channel, so that you will regularly keep receiving our new videos. Thank you, bye bye.